Hello, so today we're going to be going back to kindergarten. Well, not entirely kindergarten. We're just going to be talking about counting, and as you've probably encountered before, we're going to be first discussing the decimal system. And I'm hoping and very much crossing my fingers that you recognize precisely what I mean by the lovely decimal system, and by that I mean counting in base 10. You have 10 fingers, you have 10 toes. Whenever you give, whenever you pay the cashier at a grocery store with quarters in your pocket, you are using the base 10 system. If you ever typically, when you encounter math in the elementary, the middle school level, you'll be counting in base 10. And exactly what do I mean by base 10? Base 10 refers to the usage of these 10 digits, your 10 fundamental digits, these 0, 1, 2, and going up all the way up to 9. Right, these are 10 digits, and if I wrote the number 1423, I can express that in terms of 1000 plus 400, and this is first grade kind of level things, and hopefully you've seen most of this before. This can be broken down, and this actually arises as a result of the place values. So this is just 10 to the 1, you're taking the digit, 10 to the 0, you're taking the digit in that place, 3 here, and you're multiplying it. So 3 times 1 by the value of its position, right? And here it's 10 to the 1, so you're taking it once again. So 2 is in its position, and its value is 10 to the 1. And there's 4 here. 4 is in position. Here it's 10 to the 2. So 4 times 10 to the 2. And once again for this last one, 10 to the 3. And it goes on and on. So plus 1 times 10 to the 3. And basically these two here are equivalent. So why bother with understanding the structure of this decimal system? You've hopefully encountered it, early on in your mathematical careers, and it's pretty straightforward. And actually, the same structure can be applied to so much more than just the decimal system. Granted, the decimal system and the idea of using base 10 was initially proposed about 3000 to 1600 BCE. Granted, 0 did not and was not an actual value at the time, but the usage of 10 digits was actually pretty common as a part of Egyptian hieroglyphics. The Babylonians used the base 60, and that's where you might see 60 minutes, 60 seconds, and that sort of time kind of mess that we have right there. But long story short, people have always been fascinated with this idea of a repeating structure. When you look at Roman numerals, you have ones and you have fives and you have hundreds and fifties, but you're able to discern a structure in each of those different symbols represents value. So if you want to communicate with a computer, and computers use what is known as binary notation, you're going to have to be able to understand exactly what this binary notation, these numbers, mean. And so basically this video is going to walk you through a demonstration of conversions and really briefly touch on what I mean and what we mean when we talk about being able to communicate with a computer. So classical computers, and we'll be focusing on that primarily in this time around, classical computers use the binary system, meaning that it's written in base 2. And by base 2, that means you only have 2 possible digits. And so this usage of only 2 possible digits means that the structure itself is not going to be written in terms of powers of base 10, but if these were your place values, it would be 2 to the 0, this would be 2 to the 1, 2 to the 2, 2 to the 3, and so on and so forth. Just like how in the base 10 system, this was actually 10 to the 0, and 10 to the 1, and 10 to the 2, and 10 to the 3. So going on from there, and let's construct a table using some nice colorful marker. And let's say this is 2 to 0, this is 2 to the 1, 2 to the 2. These are just the values of their places. And going on from there, you're able to see that whenever you insert a certain value, so let's say 0, 1, 1, 0, 0, 1, and this is your binary number right here. This is your binary number, right? And you insert these values, you're able to take 0 times place and take the 1 times whatever place it's in, and you're able to add them together and convert it to base 10. So in this case, this number right here, 01101, in terms of a base 10 system, would be 0 times 2 to the 5, which is 0, plus 1 times 2 to the 4, which is 16, plus 1 times 2 to the 3, which is 8, plus 0 times 2 to the 2, which is 0, plus 0 times 2 to the 1, which is 0, plus 1 times 2 to the 0, which is 1. And we're basically just using that same computational pattern that we established earlier with the decimal system in order to convert from a binary number from base 2 into base 10. And I say base 10 just because this is the typical kind of system that we use when computing. And so in base 10, 011001 is equal to 16 plus 8 is 24 plus 1 is equal to 25. And once again, if you want to convert it the other way around, say you have a value like 11, right, and you want to convert 11 into base 2, then that becomes a slightly different task. In this case, you can express it in the sum as the sum of 1 plus 2 plus 8. And then if you take that, and if you go up here, you recognize that instead of, say, having a 0 here, 1 here, 1 here, 1 here, you have, let's see, it's filled in at 1, right? And you have a value at 2, and you have a value at 8, and everything else is 0 because that is not a part of the sum. Then in this case, your binary number as a base 2 number is 0, 0, 1, 0, 0, 1, 1, right? That's 11 written as a binary number. Alright, you might say, so now that you've hopefully grasped the concept of just basic conversions back and forth, and if you're slightly confused, of course, there's practice out there. There's also ways of writing this, of communicating this not to the computer, but with other humans. And actually, if you want to get into the mathematical portions of these transformations that can be applied to these binary values, it's important to keep in mind that you can represent them. One can represent them in a certain fashion. So let's take that previous example that we had, 11, right? Written as 001011. And let's write it as something else. Let's write it as a vector. So this is, there are a total of 6 places, so let's write it as a vector that looks like this. Oops. And because we're writing that drop down, this would be your vector, right? And that's your binary number expressed as a vector. So here, right, this corresponds to 2 to the 0, this corresponds to 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and 2 to the 5. Now, in terms of computer science, you can also be calling each one of these places, the 0 and the 1, whether it's in that state. You can call this place, you can call that a bit. Here, again, you can call that a bit. This is another bit right here, and each of these are bits. And keep in mind, we're talking about classical computers. And so, with each of them being a bit, them being either 0 or 1 determines and describes the state of that bit. And so, as a result, when you have 5 bits, these different values that can result from all the possible combinations of zeros and ones will actually correspond either to a physical manifestation on your classical computer or just some computation. And that's how the information is stored in the computer. It takes all these different possible sequences that you can have of these numbers, and it stores them in this numerical form. So with that in mind, let's start considering how to write this. So something that Dirac kind of proposed, and he actually proposed this with the focus of quantum computers in mind, but because we're facing classical computers and building that foundational knowledge to be able to understand quantum computers a little bit later, let's keep it a little bit simple. And so he actually decided to contain these values inside this, and it's often referred to as a ket. Right, it looks a little bit like an arrow. And so, in this case, he decided to contain 1 bit inside each ket, starting with the foundational basics. So in this case, it can be written as 0, 1, 0, And let's shrink this a little bit. Can be written as 0, 0, 1, 0, 1, 1. Yes? And so these 6 bits, right, describe the state of whatever you're considering in this case. Of course, writing all these symbols can get a little bit tiring. So a second way of representing it has been proposed, and it is to just write it all as 1. Right? And so say if you have a 3-bit system, then all your possible states can be written as, this is your 3-bit system, can be written as, say, 0, 0, 1, or say 0, 1, 0, or say 1, 0, 0, and going on from there, and considering all the possible states, 0, 1, 1, 1, 1, 0, 1, 1, 1, oops, 0, 0, 0, 1, 0, 1. Alright, those are 8 possible states. Right? Expressed in terms of this notation. Of course, there's one final way that you can use to describe, assuming that we're just going to be writing in terms of binary. We can actually write it instead of, let's take this example right here, right? This is equal to 0 plus 2 plus 4, which is equal to 6. This is the value of 6, right? You can actually just write it as 6. But wait a second, you might say, it depends on, what it represents can depend on exactly how many bits you're trying to incorporate into this system. So in this case, there's only 3 bits. But what happens if you had a 5-bit system? Would something that looked like 1, 0, 0, 1, 1, 0 be the same thing as this? And the answer is no. So in order to make sure we have the distinction between how many bits are in the system and how many you're considering, exactly what you're looking at and what vectors and what you're trying to describe, you can write a little subscript here, because if we're looking at 3, you write the 3 here. Yeah, long story short, this is the very basics of considering binary numbers and how to write them, etc. Of course, it is worth noting that the exact direct notation as this sort of writing of these vectors and of the values and the bits can be called direct notation. Oops, I apologize. Direct notation actually is much more complicated in that it does incorporate the wave function, so on and so forth. But once we get into quantum computers, we will describe that a little bit more in a bit more detail. If you'd like to learn a little bit more about computing, especially, and if you want to dive into quantum computing and get out of these basics, make sure you visit the Q-munity website, qmunitytech, for additional information. Have fun learning!